Okay, at some point I think we lost the stream.
Okay, at some point I think we
Again,
lost the
if y'all
stream.
notice that happen, make sure you type into
Again, if you'll notice that.
the chat, because you can still chat to me even though the video is offline. Make sure you type something in there so that we don't go too far without me fixing that. So apologize for the gap that's now in this lecture. But I think we missed about 20 minutes there. So just to put up my page on question 14D. Feel free to pause that video at any point when you relook at this. And then the conclusion of 14D was mainly calculation. Okay. All right. So now we're looking at problem 38 at page 462. Okay. So I'll just start over here. We have y equals cosine of 2x, given y equals 0, x equals 0, and x equals pi over 4. Again, what I recommend with trig functions, especially like cosine or whatever, I think it always helps if we just pick a few points to plug in and use those to kind of figure out where the graph actually is. Now, in this case, we know our boundaries are from x equals 0 to x equals pi over 4, and I went ahead and picked one more point in between, pi over 6 in this case, since that's between 0 and pi over 4, and we'll use that to give us an extra point of reference in between. Now we know the cosine graph has basically a sine wave type look to it, so we already have a basic idea of what it's looking like. But I went and plugged in 0, pi over 6, pi over 4. We got our three values for the cosine of 2x. Plot those, and so this gives us an idea of where our cosine of 2x curve is located, and from there we know that y equals 0 and x equals 0 are the other two boundaries, so this is our shaded region that we're looking at. Okay, so we know we're going around the x-axis, and so our radius, first of all, we're only going to have one radius. This is a disk method, because the shaded region is completely connected to the axis of revolution. There won't be any holes there when that's revolved around. So we have a disk method. And because we have a horizontal axis, we know we're using x variables. So r of x in this case, this is our radius function. It's basically the distance from here, 0, up to the curve cosine 2x. We take the top edge minus the bottom edge, cosine 2x minus 0. So r of x is just cosine of 2x. Okay. So from there, we set up our integration. So our volume is pi. We'll integrate from 0 to pi over 4. And we have cosine of 2x in parentheses squared dx. So from here, we'll go ahead and square, so we know we have cosine squared of 2x. And so from that point, now we need to do our integration. Now, we talked about how to integrate sine of x and cosine of x, and we know that there's basic formulas for that. Integral of sine is negative cosine. Integral of cosine is positive sine. Now, when it's 2x, we know that changes it slightly, but what's more significant here is the fact that it's squared. With a trig function squared, especially sine or cosine, it actually turns out that we cannot integrate these. Okay? At least we can't integrate them the way they currently are. So what we end up having to do is use an identity to replace these. So when we have cosine squared of u, this is identical to 1 plus cosine of 2 times u divided by 2. Okay? In this case, u is actually 2x. So when we do 2 times that, we'll put a 4x in here. So it's 1 plus cosine of 4x all over 2. Now, this 2 on the bottom, well, we'll fix it in a second. So again, the reason we did that is we cannot integrate cosine squared. You may be tempted to use like a power rule or something, but it really doesn't apply to trig functions. There is no power rule for trig functions. So the integral of cosine squared is definitely not cosine cubed over 3. That's a very wrong answer in this scenario. We want to make sure anytime we have cosine squared or sine squared that we use this identity. We have a similar identity for sine squared, except it has a minus between instead of a plus. This is what we call our power reducing formula, if you remember that from trigonometry or pre-calculus. We'll talk about this a little bit more in the beginning of chapter 8. So when we come back to this topic of working with integrals of trig functions and products of trig functions. Okay. So this 2 on the bottom, we can just factor it out and put it on the outside with the pi. So we have pi over 2 out here. And then we have 1 plus cosine x 4x. Now we're ready to actually do our integration, because while we couldn't integrate cosine squared, we can definitely just integrate regular cosine of an angle. So our integral of 1, of course, is x. What is the integral of cosine of 4x? Anyone recall? Normally we say the integral of cosine is sine, but if the angle is something besides just plain x, we have to take that into account as well. So the integral of cosine 4x would certainly still be sine of 4x, but because we have an angle of 4x inside, we'll need an extra 1/4 outside that sine of 4x. Okay. Last thing we have to do now is plug in our limits of integration. Sorry about that. Okay. So our volume, we'll plug in pi over 4 first. For x, if we plug in pi over 4 here, 4 times pi over 4 is just sine of pi. Then we plug in the 0. We know x, if you plug in 0 for x, it's just 0. We do want to make sure we evaluate the trig function, because depending on which function it is, it's not always 0. Often, but not always. Okay, so here we plugged in x equals pi over 4, and here we plugged in x equals 0. But, I mean, in this case, working out these different values, we end up with pi over 4. Sine of pi is 0, and sine of 0 is 0. So it turns out we get a lot of zeros here, so the only meaningful values we get for our volume is pi over 2 times pi over 4. So our volume is actually pi squared over 8. Okay. Any questions on that? And the other topic we'll introduce today is called the shell method. This is actually section 7.3. And we won't get a chance to do too much with this, but we'll at least get through the basics. We'll get the formula sorted out, and we'll go from there. Okay. So, with the shell method, this is another method for finding volumes of shapes that are revolved around different axes. So it's kind of an alternative to the disk or washer method. Myself specifically, if we have a vertical axis of revolution, then we can use the shell method a lot of times a little bit more easily than we can use the disk or washer method. Not 100% of the time, because there will be some problems that really just require us to do it the other way. But at least for now, as we're looking to learn these different approaches and these different formulas, I think it's a nice way to look at it starting off. So in order to use our x variables, we know that we can use disk or washer with a horizontal axis, or a shell method that has a vertical axis. So if we have a horizontal axis, we know we can use a disk or washer method. That will keep us working with the x variables. Or if we have a vertical axis, we could use the shell method, and that will keep us working with the x variables. And I think that's a nice way to start off. If we want to use the y variables, then we basically switch disk washer with the vertical axis, or shell method with horizontal axis. So they basically flip-flop everything. So that means with the shell method, let's focus on a vertical axis and see what we can do with that. As an example, this is one I really like to use for the shell method. Let's see, we have y, let's say y equals, I'm going to go ahead and use 2 over x from x equals 1 to x equals 2, and we also have a boundary of y equals 0, and it's going about the y-axis. Okay. Now the graph y equals 2 over x, this is what we call a hyperbola graph. And technically it's on both sides here. But most of our focus, if you look at all of our other functions we're given, x equals 1, x equals 2, y equals 0, that's going to ensure that we end up focusing on this portion as right here. Okay. So we don't even have to worry about this part of the graph on this lower left side. This is actually our shaded region that we're working with. Okay. So there's a little bit larger view, kind of focused in on our shaded area. Now, what's going to happen when we revolve this around? Well, we know it's going to be, it's going to make two circles, basically, a hole in the middle and then a larger circle outside of that. So it's going to be like a 3D washer almost. And if not for these flat edges, we'd almost be getting into donut territory anyway. But that's kind of the concept that it ends up creating. Now, with a disc or washer method, we focus on what are the radii, or the two different radius that we use to revolve this graph around this y-axis. But with the shell method, it's actually a completely different approach. We're no longer looking at it in terms of discs or washers. We're no longer looking at circles. Well, technically, we're still looking at circles, but in a different direction, I guess. But the idea is that we want to create a series of concentric cylinders. So that means the cylinders are all fitting inside each other. And they're kind of stacking up to create the volume that represents this object being rotated. So, to illustrate that a little bit further, let me go to the next page. So here's our shape again. And so what happens now is that each x value here, from 1 to 2, we're creating a different cylinder. We call it a cylindrical shell. Okay. Basically, we don't want the inside filled in. We just want the outer, the exterior part of the cylinder. Now we create that for each x value that we have. And so what's going to happen is that we end up with just a bunch of these cylinders kind of stacked together inside of each other in this case. Okay. So we have kind of a taller cylinder inside, and we gradually add cylinders outside of that. They get shorter and shorter. Okay, so basically all of these cylinders are hollow, so we just have the outside part, and we're stacking them up together, so collectively they still, all these different cylinder pieces still add up to the total volume of the object being created. And in that sense, that's why it's we still have that connection to the Riemann sums, is that we end up adding all those different areas together to set it equal to the volume of this 3D object. So if we look at a cylindrical shell, just one shell by itself, we know we have to worry about the radius and the height. And again, this is empty inside, so we don't want the volume inside. We just want this outer edge area, the what we call the lateral area of the cylinder. And so the lateral area, basically what we do is we take the circumference of the cylinder. So our lateral area, This is the circumference times the height. So a circumference, that's the circumference of a circle, so it's 2 pi times the radius, or pi times the diameter, however you remember that, but we're going to be given the radius, or we'll have to find the radius, so we'll use r instead of diameter. And then we'll have height, which is h. And so that's the lateral area of the cylinder. And so what we're going to do is add all of those cylinders together, which means we basically convert it to an integral, and we can do that to help us find the volume. Okay. Now, you'll notice, looking at this graph, and it may be harder to see now that I've drawn all over it, our cylinders start at x equals 1. Here's our first cylinder on the inside, and they continue until we get to x equals 2. So one of the things that's different about the shell method is that our limits of integration are based on where the graph actually exists. So in this case, x equals 1 to 2, this will be our limits of integration, 1 to 2, and then inside we'll just take this expression, 2 pi r h dx. So we want to add up all of those cylinders, areas from 1 to 2 with respect to the x variable, and that's what the definite integral represents in this case. Now, r is actually going to be a function of x, and h will be a function of x. Now, in the context of these cylinders, x is the distance from the axis of revolution, or sorry, r is the distance from the axis of revolution to the individual x values here. Okay? Because the radius of the cylinder basically says, okay, it depends on how far away the cylinder that we're creating, how far away the edge is from the axis, in this case 0. And so we said, okay, from 1, we know that if we're at this edge of the shaded region, we know we're 1 unit away from the axis of revolution, so it has a radius of 1, and on this side we have a radius of 2. But basically what happens is we get all the values in between also. So whatever the x value is here for each of these points, that's how far we are away from the axis of revolution. So r of x in this case is just equal to x. Now the radius function in shell method problems is always just going to be x, and then sometimes plus or minus a number if our axis of revolution is shifted left or right of the original vertical axis, the y-axis. Because we're right on the y-axis, we don't have to modify this by anything. Our r of x is just x. Okay, so if we're at an x value of 1.25, then we're 1.25 units away from the axis of revolution. that'll be the radius. So each x value is actually its radius to the origin, or to the axis. Now the height function h, this is the distance from the top to the bottom of the graph, or top edge to the bottom edge. Okay. So h of x in this case is this vertical component. Now, it may be, depending on the problem, that the top edge is one function and the bottom edge is a different function. In this case, our bottom edge is technically 0, and so our function here, y equals 2 over x minus y equals 0. So we'll use h of x equals 2 over x. And that'll be our height function. So finally, we know volume is 2 pi integral a to b of r of x times h of x dx, which for this particular example, now a to b are limits of integration. That's just going to be 1 to 2 because our shaded region exists between 1 and 2. And then r of x we said was x, h of x is 2 over x dx, and from there we'll just keep going. It ends up being that the answer is, I believe it's 4 pi. Because what happens is x times 2 over x cancels out to a 2. We integrate 2 to 2x, plug in the limits. 2x times 2 is 4. 2x, or sorry, 2 times 2 is 4. 2 times 1 is 2. Subtract, so we get 2 times 2 pi is 4 pi. So yeah, that's correct. I'll figure out what problems I wanted to look at. So for homework, page 461 first, 5, 7, 13, 37, and I won't assign any just yet for the shell method, so just work on the disk and washer method problems for now. Go ahead and add 15 in there, since we're just working on that one section. Alright. So go ahead and go through and practice those problems. Again, let me know if you have any questions. And again, if we end up in a situation where the stream cuts out partway through, make sure you put something in the chat, because you'll still be able to type into the chat and I'll still be able to see it, even though you're not able to, you may not have any video. So just let me know when that happens so we don't have like a gap in the lecture. But anyway, I hope you all have a good rest of the day. Take care of yourselves, and I will talk to you again on Thursday. Bye.